Lab 3 Magnetic Field of a Bar Magnet by Pablo Vila. The purpose of today's video is to measure the distance dependence of the magnetic field due to the bar magnet and compare the true distances with the predicted distances from the PHYS law. We also want to understand the magnetic fields through a visual representation, and we'll do this through GlowScript. The main lab results we'll see by the end of this video is that 1. When a magnetometer is far away from a magnet, Bx approaches 0 Tesla, and when a magnetometer is approaching a magnet, Bx increases. We also see that n in our experiment is equal to negative 2.8438, and our mu is equal to 4.57 amps times meters squared. The main physics ideas that are present in this experiment include the PHYS law off-axis, which can be seen in the equation below. We also need the dependence distance formula B bar equals k times r raised to the n, and we will also need the linearization formula, natural log of bx equals natural log of k plus n natural log of r, so that we can graph our data. The main procedure in this experiment was downloading a magnetometer app on your phone and locating where inside the phone the magnetometer is located. Next, we line up the phone towards north, which can be found by rotating the phone until Bx is 0. Finally, the distance between the chip and the bar magnet were measured in various locations, both on axis, perpendicular, and off axis. Some of the initial conditions include the phone alignment with north and the bar magnet aligned with the magnetometer. The system in this experiment is the bar magnet, and the surroundings are everything else. Here is a sample of some of the data I acquired from my experiment. The far yellow column represents the on-axis distance from the bar magnet at various magnetic fields. The right yellow column are the values of the magnetic field. The blue columns are averages of the distances and the magnetic fields. Next, the data was linearized and graphed using the equation above, and the slope-intercept equation is seen on the right. In this data, we measured the perpendicular distances of the bar magnet at varying magnetic fields. We also found By by Earth, based on the latitude and longitude of my location. Finally, we corrected By due to Earth. One thing we noticed in this data is that Bx approaches 0 at large distances. Calculations were performed to find n, natural log of k, and k. This was completed through the linearization equation. The value of n is found from the slope equation earlier. Mu was found through the dependence distance formula. We assumed that r was equal to 1 meter, and we found that mu was equal to 4.57 amps times meter squared. In this first part of the code, some of the initial functions were defined, such as mu over 4 pi, which is 1 times 10 to the negative 7th. Mu hat was also defined in line 21, and mu magnitude was defined in line 24 as 4.57199, which is something I found in my own experiment. And we also defined the dipole function, which is defined using the PHYS formula. And finally, we defined the scale and distances of bar magnets. In the second part of the code, 2 arrows were drawn on axis to the magnet, 4 arrows were drawn perpendicular to the magnet, and 1 arrow was drawn off axis. For each arrow, a position, axis, and color was defined. Finally, the values were all printed so that we can see what is going on. Some of the similarities we'll see with the code and real life is that the on-axis vectors point in the direction of mu, while the perpendicular vectors point opposite to it. The major differences we'll see is that the experimental B net was found to be approximately 6.45 e to the negative 5 Tesla, and the theoretical B net was approximately 4.53 e to the negative 5 Tesla. This is a roughly 70.25% difference. So what if you hadn't oriented your experiment to compensate for magnetic north? Then the Earth's magnetic field would have interfered with the bar magnet's magnetic field, and the results would have been skewed. And what if you were to stick the 2 magnets end to end and run the experiment? Well, we would have seen that the magnitude of the magnetic field would have roughly doubled, but the direction would have stayed the same. In conclusion, the bar magnet can be modeled as a magnetic dipole, and the magnetic field increases as you get closer to the magnet. Some potential sources of error in this experiment include the magnetometer not oriented to north correctly, the location of the magnetometer inside the phone was off, and there were electronics present in the room that could have skewed the data.